8.2, we're going to take a look at the mean and the standard deviation of a random variable. Remember, we're talking about discrete random variables here. So the formula that you're about to see here works only with discrete random variables. So our first formula you see here is that of the mean or average of a discrete random variable. So the way this formula works, and we'll see example here in just a moment on how this actually is going to work. The formula looks at, and it's made up of xi, x subscript I, times probability of xi. So what this expression means is that you multiply the outcome times the probability of outcome of the random variable. Okay, and that's what this formula does. And sigma means you do this for all outcomes. And note also, by the way, here I have mu equal e. E here stands for expectation. So the mean of the random variables, we often call them expected value of the random variable. Now the expectation, the way it works in probability, the expectation means if you do this process over a long period of time, this is what the value of a random variable you would expect to see. Okay, so that means, for example, if you observe the value, if you were to observe the value of random variable over a long period of time, this is the value that you would expect to see. Now, no one defines what a long period of time is. Theoretically, it's infinitely many. So it's just over a very, very long, stretched out period of time. Okay. So that's what the formula is for the mean of the random variable x. And sometimes we actually use mu and then we subscript it with the name of the random variable, in this case like capital X. So that means that works if you have more than one random variable, so I know what mean it is that I'm finding here. So I tend to do that later on. So here's an example. Remember the example we had for number of fatalities on the 4th of July. Let's say we want to know what could come next 4th of July. How many fatalities in that city should we be expecting? So here's our formula. Sigma x px. So that means I need to multiply x. X is the outcome, right? And px is probability of outcome. So I've written this down as using subscript I, that's x1, probability of x1, x2, probability of x2, x3, and x4, because there's only 4 outcomes here. Okay, now putting the specifics into this, so I'm going to multiply 0 times probability of 0. That's what this part is. And then you multiply 1 times probability of 1, 2, 3 times probability of 3, and so on, and that's how you get the numbers down here. Okay, and sigma means, the sigma here means add them up. So when I add them up, I get 0.7. Now we expect 0.7 fatalities. Now how can that be, right? How can you see 0.7 of a fatality? Well, and I have it down here. You can go about it this way. You can interpret it actually, if it makes sense, do it this way. One is the way I have it. If you move the decimal in front of 0.7 to the right, you get the number 7. Now remember, this is for a given 4th of July. Now 0.7 becomes 7. That's like multiplying it by 10. So one way I can describe this is that I would expect 7 fatalities in the next 10 4th of Julys in this city, right? Or another way to characterize this is to say I would expect to see 7 fatalities in 10 cities on next 4th of July, as long as these cities, 10 cities, are comparable. So if I'm looking at San Diego, I gotta find a city that's like San Diego. or if I'm finding this for a particular zip code even, then I got to find places that are very comparable to this. So that's how you can get around the interpretation of the decimal. Okay, so that's all we're doing here. Now StatCrunch will do this for us. I just want to go through the motions with you. My example later on, we're going to carry on the number of people living in a household. We're going to do that one, and we're going to use the StatCrunch on that one. Now, in case you wonder, I think it was in chapter 3, but let me take the chapter out of it because I'm not sure. So in an earlier chapter, okay, so there is a connection between the formula let me just call it in earlier chapter and in this chapter. Okay, so how are they connected? Well, in chapter 3, I believe it was, again in that chapter. So let me just say, so we want to show that the formula we had in the earlier chapter is the same as the formula that's in this one, special case of this rather. Now, this should be familiar with you again. We looked at this formula before. That's the population formula. You add up all the score divided by the total, right? Now, with that formula, we make the assumption that every observation is equally likely to occur, right? So the associated weight or probability that we observe each of those observations is 1 over the population size. So if I have, in a city of 3 million, probability that I will be selected for the survey would be 1 in 3 million. And every one of us will have an equal chance, an equal probability of being selected. So this actually becomes a probability distribution. So you have n scores, and 1 over n is the probability of any one of those are selected, and assuming sampling is done, of course, with replacement, so the probability of 1 over n is not going to change. Okay, and if I carry on, the formula is simple. It's not too difficult. You can follow, I hope. This formula becomes what we've seen earlier. I just want to show you the connection between them. Again, if you don't follow this, that's okay. But there is a connection between them. Now, so what that means is this. If I want to find the mean of this distribution, this one, it will be incorrect if I do 0 plus 1 plus 2 plus 3 and divide it by 4. If I do that, I get 6/4, which is 1.5. The average turns out to be 1.5 fatalities, whereas realistically it's half that, right? So that would be incorrect way of finding the average. That doesn't work in chapter 5 with discrete probability distributions. Now, the formula for the variance is given also. Here you have the formula for variance, and I'll do example of that in a moment. For the variance, you do x minus mu squared times probability of x, and you add them up. Okay. So again, in earlier chapter, I guess it was chapter 4, but let me fix that. Okay, I fixed that one. So there are similarities between the formulas that we saw in earlier chapter and the formula that's above. Okay. But I won't show you the formula, but there you have it. Now, there are two formulas here, and they're really the same. One is what we call conceptual. This is actually conceptual formula, not computing. So we have these formulas. One is called the conceptual formula, and the other one is computing formula. Okay. And the conceptual looks at the deviation from the mean. Remember, x minus mu is a deviation of observation from its mean. That's, in that sense, is conceptual. So this is the conceptual right in here, and this is the computing formula. Computing means do it this way is easier. Conceptual means think about it this way when you do it. So let's take a look at an exercise now. The example we've been carrying out with. So we want to calculate the variance using both conceptual and computational. First, using conceptual. Remember, we have to calculate the deviation from the mean, then square it, right? Once we square it, we multiply by its probability. So that's what I've done here. 0 outcome minus the mean, which you calculated just a few minutes ago. You square it times its probability. And you do that for every one of them. Outcome minus the mean squared times probability. Outcome minus the mean squared times probability, and so on. And once we do this, then we have the variance is 0.81. The units on variance are in square units, so we don't like that. We're going to take the square root of it and change it into standard deviation, and then we will interpret that. Now, using computing formula, you do this portion of the formula first, that part. So you square the score is the outcome. You square the outcome times its probability. You square the outcome times its probability, and the next one, and the next one. And then you add those up, and then once you've done that, you subtract square of the mean from it. So I have done that. I have done that down here, and you can kind of see now. I got 0.81, also the same as the number that's directly above that. Okay, so both will work. Now for interpretation, again, we'll take the square root of the variance, and it gives me the 0.9. That's square root of 81. And now we can interpret the 0.9, again, just like we did the mean. Because 0.9 of an accident doesn't make sense, we can move the decimal, turn that into 9. And say that we expect, on average, remember we said we expect 7 fatality accidents in 10 cities, like the one that we sampled. Give or take 9, which is quite a bit. I mean, give part adds another 9, that makes it 16. Take actually takes it into negative territory, right? 7 minus 9 is -2. That's the takeaway from 7. Now we can't say we have negative accidents, right? So I would expect anywhere from, in 10 cities, anywhere from 0 to 16 accidents, which is wide range. It is rather wide range, but it is based on this data. So, and with that, let's finish this off with the housing units. We did this in section 5.1. Okay, this exercise where we found the probability distribution in StatCrunch. Now, the output from StatCrunch, I can show you that output. I still have it, I think. Yes, right in here. So remember, this is what the output looked like from StatCrunch. And I just copied the top portion in the previous section, but there's actually a bottom portion to it here too. I showed you how to find some probability statements, right? How to find probability for events. But right in here, this is where the mean and deviation are given in StatCrunch. Okay, so again, to show you one more time how you get the mean and deviation, since we moved away from that section. Once you have the distribution, you go to Stat, Calculators, and then you go down to Custom. And then the values are in variable person. The probabilities or weights are in the probability column, compute, and there you go. This is what you get. That's the default. You can change these probabilities to whatever you like and get a different probability of different event. But the shape of the distribution is what we want actually. And there you go, that's the shape. And in this section, section 5.2, again, the two key components for mean and deviations. And that's what I carried over to my note. So you can kind of see now. So the mean, the average, the expected number of accidents, we would expect 2.5 accidents. That's 25 accidents in 10 cities, because this is per city for one city. 2.5 in one city is equal to 25 in 10 cities. And give or take 1.4, that means 14, give or take 14 in a city. Okay. And oh, I'm sorry, this was an accident. Sorry, this is number of housing units. I'm still thinking my own example. Sorry about that, folks. So let me clarify. These are the number of people living in a housing unit. So we expect 2.5 persons live in a housing unit. Okay. Now, again, how can I have 2.5 persons living in a housing unit? That's impossible. So move the decimal. That means 25. About 25 people in every 10 households. Give or take 14. That's 1.4 times 10. Give or take 14 people for every 10 households. Okay. Now that makes sense. Again, I apologize for my interpretation as accidents because I was still up here working with my own example here. Okay, and with that we are done with this section 5.2, the mean and deviation of the random variable.